So in the next problem, I asked us to sort the same set of numbers using the bubble. So the logic of the bubble sort is to make n passes through the list when sorting n items. Each time you make a pass, you compare the item at the current position with the next position. And if they're out of sequence, you swap them. So the things that we're sorting is the same set.
31, 71,
23,
73,
depending on you this time.
29, 91, 79, 53, 47, 37.
Alright, so that's before it starts sorting. Now, after pass 1, I'm just going to do pass 1 on the board, swapping if necessary. Now, pass 1, let's say we're sorting in ascending order. So compare 31 to 71. And they're in place, I don't need to swap. 71 to 23, I swap. Alright, let me just write down 71, 23, compare. So they're out of sequence, so I swap 23 and 71. Now the next item that was there will be 73. Compare them. They're in sequence. Next item that's there is a 29. Comparison. They're out of sequence. I swap. So I end up with 29, then 73. Then the next one there is 91. And next one there is 79. Compare. Realize that we need to swap. Next one there is 53. Compare and swap. Next one there is 47. Compare and swap. Next one down 37, compare and swap. Now, after each pass in the bubble sort, we can see that the heavier items, where if we think of the large items as the heavier items, the heavier items will bubble down to the bottom after each pass. So after n passes, we'd have seen that the list will be fully sorted. Now, in one pass, how much work would we expect to do if we had n items?
N minus 1.
We can do up to n minus 1 steps, comparisons and swaps. So one pass is a theta n process. We have up to n passes, so therefore the order of growth of the bubble sort is theta n squared. So both the bubble sort and insertion sort are theta n sorts. And the next one we're looking at is on tutorial 7.
Did we left that now?
Oh, you got through and did the whole thing, but
So you'd have to go back again.
right. That's, you understand how to do that. It's not complicated. It's not interesting anymore. In the tutorial, we're just asked to go through the steps. We're going to have to write in the code. Now, in tutorial 7, do you have a copy?
Yes.
Nobody has a copy?
I have.
Alright, and hopefully they can share. So, the insertion and the bubble sorts will both have theta n squared performance. But when you're sorting a lot of things, millions of things, then theta n squared performance might mean that if you have 1,000,000 items, then 1,000,000 times 1,000,000 is a big number, right? So we don't want our computing power to have to work with that number of computations if we have better options, and we do. Now, a simple option could be attained by using the heap sort. If we decided to take the items we want to sort, put them into a heap, then read them back out. Remember that as long as you put something into a heap, then you're going to take up to theta log n time to put one thing in, and theta log n time to take it out. So we're putting n things in, then we're going to take n times theta log n to put everything in, and n log n to take it out in the worst case. So simply copying everything into a heap and reading it back out, and making sure that once we read it back out, we maintain the order, does a good job of sorting the thing in much better time than we can get from the insertion sort or much better worst case time than the insertion sort or the bubble sort. One thing I must point out is that while the insertion sort has a worst case time complexity of theta n squared, as we saw, sometimes when we're inserting, we really didn't need to do any work. So in the average case, the insertion sort works out pretty well. Now, another theta n log n sort that we looked at was the merge sort. And that's really sorting by delegation, meaning that the way the merge sort works is that if you, or something has a list of n items to sort, then that set of items is split into two, and each part is given to something else to sort. Now, that other thing will sort that n upon two things using the merge sort. The original sorter knows that it expects back two sorted lists, and the only work it has to do after that is put back those two sorted lists together. So it now knows that it just needs to depend on two merge sorts and the time to put the things together, which would be a theta n process. So we're going to look at an example showing how the merge sort splits and puts the lists back together. We're going to be sorting the same steps. And to split this list, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 items. So 5 will go into the first set. So in the first set we have 31, 71, 23, 73, 29. Second set we have 91, 79, 53, 47, 37. To sort that list, we're going to first split it and depend on something else to sort it with the merge sort. So this ends up with a list with 31, 71, 23, another list with 73, 29. Over here, we split our list into 91, 79, 53, and then 47, 37. So here, we're going to split again. 31, 71, 23. Now, when we have two or less things in the list, it doesn't really make sense for us to split the list again. All we do is check and see if the items are out of sequence, and if they are, we swap them. So we'll do a swap here, so we end up with 29, 73. This one needs to be split before we start sorting it. So we have 91, 79, 53, And these are out of sequence, so we're going to just swap. Alright, we have some lists with only 2 items. We're just going to check and see if they're out of sequence and swap if necessary. These are in sequence, that's good. Something by itself. Already swapped. These need to be arranged. So we have 79, 91. And we don't have any more swapping to do, but now we need to start putting back the list together. So these two are going to come back together. Now while they're putting them back together, the process looks at the first part of each list. And then the smallest thing is then added to the new list. So in putting these things back together, smallest thing here is 23. Then the 37 and 71 come in. 31, 71. We're going to merge those two later. In fact, since we're over here, let's just finish merging this part here. And then merging these two back. Smallest thing there first is 23. Then we have smallest thing of the beginning of either list is 29. So that's the next thing that's going to be written to the next list. Then we have the 31. Then the 71 is the smallest thing out there. Then 73. In merging these, first this list has to be merged, 53, 79, 91. And then we can merge this part with this part here. So the smallest thing out there is a 37. Then comes the 47, then the 53, then 79, then 91. So then we need to merge these two. So first you have the 23 as the smallest thing out there, then 29, and we'll keep on finding the smallest things from either list. 37, then 53, then 71 will be the next smallest thing, then 73, that's how the merge sort works.